Hey everyone, welcome grade 7 students and curious learners everywhere. I am absolutely thrilled to have you join me for today's explainer. We're going to go ahead and put on our scientist hats right now because we are diving straight into the fascinating, kind of invisible world of chemistry. Specifically, we're looking at the mechanics of exactly how and why things dissolve. I mean, if you've ever mixed up a drink or helped out in the kitchen, you've actually watched this science happen in real time. So my goal today is to give you the exact scientific framework to understand what is actually going on right before your eyes.
To kick things off, I want you to picture an everyday mystery. Why does sugar dissolve so much faster in hot water than it does in cold water? Seriously, have you ever noticed this while making a hot cup of coffee or tea or maybe some hot chocolate? You drop the sugar in, give it a really quick swirl, and boom, it's gone. But if you try doing that exact same thing in a glass of ice-cold water, well, you're usually left with this gritty, stubborn pile of sugar just sitting at the bottom of your glass. What is the secret invisible force making that difference? Keep this question in the back of your mind, because by the end of this lesson, you are going to know exactly why.
Okay, so here's our roadmap for today. First up, we'll cover the basics of solubility. After that, we'll explore the three major factors that control how fast something dissolves. Factor 1 is temperature, Factor 2 is stirring, and Factor 3 is particle size. Part 1, the basics of solubility, understanding the parts of a mixture. Before we can manipulate chemical reactions, we really need to speak the language of science. So let's look at the basic building blocks of any mixture.
In any mixture where something dissolves, you always have two main characters, a solute and a solvent. The solute is the substance that's actually being dissolved, and it's almost always the thing you have a smaller amount of. Think of that spoonful of sugar you add to your drink. The sugar is the solute. The solvent, on the other hand, is the substance doing the dissolving. It's usually a liquid, and you have a much larger amount of it. Water is literally the most common solvent we use every single day. So just remember this simple rule. The solvent attacks the solute to dissolve it.
And that brings us to our big vocabulary word for the day, solubility. Solubility is simply the ability of a substance, our solute, to dissolve in another substance, our solvent, to form a complete, even solution. Honestly, think of solubility as the rulebook. It's the rulebook that dictates just how well two different things are willing to mix together.
Now, in the real world, some substances are highly soluble, which means they dissolve beautifully. Things like sugar, salt, and powdered juice mix perfectly into water. They seemingly disappear to form this nice, uniform solution. But then there are the rule breakers. Some things are insoluble, meaning they absolutely do not dissolve. Toss sand or small stones into a glass of water, and they'll just sink and sit at the bottom forever. And cooking oil? It just stubbornly floats at the top, completely separating from the water. They refuse to mix because their particles just aren't compatible with water in the same way.
Which brings us to Factor 1, temperature, and how heat changes the game. And spoiler alert, this is going to answer our opening question.
Okay, I want you to imagine a tiny, microscopic particle party. When you look at hot water, you aren't just seeing a warm liquid. You're looking at particles absolutely buzzing with high kinetic energy. The heat makes the water particles move incredibly fast, bouncing around like energetic bumper cars at a theme park. But when you look at cold water, it is a vastly different scene. The particles there are sluggish, just kind of meandering and moving slowly because they have way less energy.
Boom! Right there, that is the secret to our mystery. Because those hot water particles are zipping around with so much speed and energy, they actually crash into the sugar particles much more often and with way more force. These frequent energetic collisions act like millions of tiny little hammers, breaking the sugar apart and mixing it into the water incredibly fast. In cold water, those sluggish, tired particles just don't collide as often or as hard, so the sugar takes much, much longer to break down. And that is exactly why your hot drinks dissolve powder so quickly. All right, let's move on to Factor 2, stirring, giving the particles a helpful push. Imagine you're making a huge, delicious glass of chocolate milk, and the powder is just sitting in a dry clump on top of the cold milk. What's the very first thing you reach for? A spoon, right? Let's break down the actual science of what stirring does. First, you stir the mixture, right? You're providing mechanical agitation. That motion forces the solute particles to spread out evenly throughout the solvent, rather than just clumping up in one sad spot. Because they're spread out and constantly moving, the solute and solvent come into contact way more frequently. We get a massive increase in collisions. And finally, because of all those extra collisions happening all over the glass, the substance dissolves significantly faster.
Think about it. If you were to drop a spoonful of salt into a glass of water and literally just walk away, the salt would, eventually dissolve. But it would take a really long time because the salt is just sitting at the bottom and only the water particles immediately touching it are doing any of the work. Stirring is pretty much the most effective manual tool we have to speed up this whole chemical process. It acts like an accelerator pedal, forcing fresh water particles to constantly attack the solute.
Okay, factor 3, particle size. Big chunks versus tiny grains. Let me ask you this. If you dropped a giant solid rock of salt into a bucket of water and then dropped a handful of tiny salt grains into another bucket, which one do you think would disappear first?
Well, to understand the answer, we have to learn a really vital scientific concept: surface area. Surface area is the total amount of the solute's exterior that is physically exposed to the solvent. And why does this matter? Because water can only dissolve what it can actually touch. It has to work from the outside in.
So let's compare a solid sugar cube to a pile of powdered sugar. A sugar cube has a really low surface area relative to its size. Why? Because all the sugar trapped deep inside the middle of the cube is completely hidden and protected from the water. The water has to slowly eat away at the outside layers just to get to the center. But look at powdered sugar. By crushing the sugar up, we have exposed every single tiny grain to the water all at once. The surface area is absolutely massive. The water can surround and attack all the tiny pieces at the exact same time, causing that powdered sugar to dissolve almost instantly.
All right, that brings us to our lesson recap and review, putting it all together. We have covered some fantastic ground today, so let's consolidate our notes before we wrap up.
If you want to force a solute to dissolve into a solvent as quickly as physically possible, here is your ultimate scientific checklist. Number 1, heat it up. Increase the temperature to give those particles high kinetic energy so they act like speedy bumper cars. Number 2, mix it around. Use stirring to constantly spread the particles and force contact. And number 3, crush it small. Decrease the particle size to maximize the surface area, letting the water attack the solute from all sides at once. At the end of the day, every single one of these factors is doing the exact same underlying thing. They are increasing the number of collisions between the particles. So I'm going to leave you with a final practical piece of homework to test out your new scientific mindset. If someone handed you a giant, rock-hard salt crystal and told you that you needed to dissolve it completely in under 1 minute, what exact 3 steps would you take based on everything we learned today? Think about it, apply the framework, and see if you can solve it. Thank you so much for joining me on this Explainer Grade 7. Keep observing the world around you, keep asking great questions, and I will catch you on the next lesson.